Thank you very much. And I want to warmly thank actually the organizers for the invitation. It's really a pleasure to be in this very nice place. And today I will talk about some very simple thing, which is, can we realize in circuit QED, meaning actually with just harmonic oscillators and qubit, so few level systems, a phase which has physical property related to the topological, the quantum Hall effect. So very simple actually quantum Hall phase, but really focusing on transport properties of these phases. And so that's really the purpose of this talk, is how to realize such a quantum Hall analog. And to do so, actually, I will revisit the transport properties of the simplest canonical topological phase, which is the quantum Hall effect. And I will show actually that we can consider the response of this phase as a particular coupling between actually probes, electrical probes that you use, which is a particular coupling between different harmonic oscillators. And then I will show how to implement this coupling with this simple circuit QED. And if time allows, at the end of the talk, I will then consider a situation where topology a priori doesn't apply, where we consider a coupling between quantum oscillators. We don't have now topological indices to characterize the phase, but yet we have physical property that share some resemblance with the topological phase. And to put that, this talk into broader context, actually we've heard in particular this morning about very different topological, electronic topological phases where whether actually insulators, superconductors are interacting phases, where we've learned in the last 2 decades how to use topology to characterize these phases. And those ideas have been extended even beyond actually electronic phases to characterize waves, optical, mechanical, or even actually heat waves at the surface of oceans using topology. In all these systems, topology predicts, promises actually some robustness with respect to a class of perturbation. And the question is, how do you measure this? What's sensitive to this robustness? And actually, at the end of the day, what you get are, most of the time, surface states. So topology predicts the existence of surface states. And the game then is to find the physical probe that's really sensitive to these surface states that you get. Today I will basically present a different way to view actually a probe, a physical probe that's sensitive to the topology, even without surface states. But to do so, let me reconsider the canonical example of a quantum Hall effect, so a phase of electrons whose dynamics is restricted in 2 dimensions and submitted to a very strong transverse magnetic field. We know that in such a phase, then you have a quantization of this Hall conductivity, which is the signature of the topological nature of your phase. One first way to relate this quantization of conductivity, transverse conductivity to topology is by looking at linear response theory. So in infinite system, you look at the to linear order, how it's perturbed by an electric field. Use, for example, Kubo formula, and you get this relation, as was done by Tholes and coworkers, between the Hall conductivity and a Chern number, a topological index characterizing the ensemble of electrons in your topology, in your quantum Hall phase. There's an alternate way, of course, to do so based on edge states. We know that because the phase is topological, we'll have edge states. Each Landau level gives rise here to chiral edge states at around your sample. And on very general ground, then that means that this chiral edge states, because you have a bulk in the sample, allows to write down the scattering matrix between different contacts, between electric contacts and your sample. You can write down the scattering matrix, and from this scattering matrix, using Landauer formula, you get the conductance. And all these transverse conductance corresponding to Hall conductivity are quantized, and basically the coefficient of quantization is the number of chiral edge states, and so the number of Landau level, the Chern number of your phase. That's the standard way out of edge states to characterize the transport of this phase. There's a third way, actually, which was really inspired by a Gedanken experiment by Laughlin, which is to say, if you consider a Corbino geometry, so a disk of a quantum Hall system with a hole here inside, and you imagine that inside the hole, on top of a magnetic field giving rise to the quantum Hall effect, you add some magnetic flux. You basically act on the electrons from a Ranoff-Bohm effect. Then actually you give rise between the inner and outer edge to a current. As this magnetic flux is increasing, a current occurs, and that's a very general argument that actually was then generalized by Fowles and coworkers and these three people in more mathematical framework to say that if, instead of looking at this Corbino geometry, I wrap the sample on a cylinder that's topologically just the same. And now this flux that was threading the Corbino geometry is a flux going through the cylinder. And so in this general actually framework, I can consider two fluxes, this first one driving the system and the second one arising from the current. And then you can write down actually the whole conductivity as being related to a Berry curvature of the many-body ground state of your quantum system, parameterized by these two fluxes. But this is this formula where I introduce here the notion of Berry curvature of any vector parameterized by two objects. So that's a priori an abstract way to relate transport properties of quantum Hall effect to a topological quantity, or here a geometrical quantity, which is going to be related to topological in a moment. But actually, I'm going to argue that this is exactly what we're doing when we're actually measuring transport properties of a quantum Hall sample. If you consider a quantum Hall sample and you want to measure Hall conductivity, you're going to connect your sample to two different electrical circuits, one in each direction, one to measure the voltage difference and one to drive a system with a current. But each electrical circuit actually can be described by an LC circuit, an harmonic oscillator. And so the two variables that we need are the flux, which is nothing but the integral in time of a voltage difference between the end of an electrical circuit. So that's these two fluxes. And I have the canonically conjugate variable, which is the charge that you've added to an electrical circuit. So now here I'm describing two electrical circuits as LC oscillators, LC circuit, and they are coupled through the quantum Hall system. So the fact that I'm going to get, at the end of the day, a Hall quantization, so a transverse current, means I'm going to couple in a specific way these two harmonic oscillators, these two electrical circuits. How do I couple actually this electrical circuit to the quantum Hall system? Then I can account actually for the presence of these two fluxes by Aharonov-Bohm properties, saying that if I consider here the many-body ground state of my quantum Hall sample, and I take the coordinate of one of the particles, one of the electrons, and I move it across the sample, then this wave function is going to pick up a phase, which is nothing but how many fluxes I had in the corresponding loop, electrical loop, in units of flux quanta. So that means that I couple to these two external variable, classical variable, in a 2 pi periodic way. So my ground state wave function is 2 pi periodic in these redefined phases, which are the fluxes in both loops, defined in units of flux quanta, and associated a canonically conjugate variable. So if I want to describe this system, the physical property of this system, on very general ground, what am I doing? I'm considering a quantum system, that's my quantum Hall sample in that case, which is coupled to, in that case, that's two harmonic oscillators, but generically I'm going to couple here to two classical systems, and I couple only to one of our canonically conjugate variable, the phase, let's say. And in that case, I couple to this phase in a 2 pi periodic way. How can I describe now the evolution of this system? Well, I'm going to assume furthermore that this quantum system is gapped, like in the quantum Hall system, and that I remain in, let's say, the ground state, in one of their energies as the variable phi1 and phi2 evolve. So you can describe now the evolution, the adiabatic evolution of this system, but instead of focusing, as we usually do, on the evolution of this quantum system, what I'm going to do is focus here on this classical environment, these classical oscillators. And I'm going to write down the standard Hamilton equation for the evolution of this bath. So I can write down on the regional ground here the Hamilton equations for the two canonically conjugate variables of these oscillators. On top of the standard Hamilton equations, because now I have a coupling to the quantum system, I need to add an extra term. This extra term originates from the fact that my Hamiltonian now depends on the phases of my two classical environment. And I'm further assuming here that I'm always considering this operator into the ground state. So I only look at the average value, the expectation value of this operator in the ground state, which is this state corresponding to this energy manifold. When you do so, you get two terms. One that you could have guessed from Hellman-Feynman theorem, the fact that your quantum system might have an energy that varies as a function of the phases, but you get an extra term, and that's very general. And this extra term is exactly the Berry curvature I was introducing. So the Berry curvature of this, the eigenstate you're considering with respect to the two phases. But actually, it has a physical meaning which is very interesting. What it tells you is that if you change the phase of one of these classical baths, then the other bath actually will have a number of charges which will increase or decrease. That means that if, let's say, you find here, you have a phase which is monochromatic, so omega 2 times t, then that means you'll increase constantly in time the number of particles here. So you're pumping charges from one bath to the other one. And that's a very general property of a quantum system coupled to two classical environments in this case. So that applies, of course, the case of a quantum Hall. So first, actually, where does topology occurs in that context? So until now, I was only considering here a Berry curvature, nothing that's a geometrical object. But actually, if your Hamiltonian is 2 pi periodic, that means actually that the parameter space that you should consider for these two variables, phi1 and phi2, is just a closed manifold, in that case, a two-dimensional torus. And I can integrate now this Berry curvature on this torus, and that gives me a topological index. This topological index means that on average now, my Berry curvature is constant. Okay? So I get a constant pumping on average when I'm topological, as opposed to purely geometrical pumping. So you can apply these ideas to the quantum Hall effect. So just exactly the formula I was writing down. You have to remember what were the phases phi and n for these two electrical circuits, and you get exactly the formula of Thouless and coworkers for this quantization of the Hall conductance. But that's not it, actually. That's not the end of the story. Now you can apply this idea to a series of systems that share the same physical properties. So the quantum Hall effect, and then a Thouless pump. A Thouless pump, that's a one-dimensional system that you drive in time at a given frequency. And then you induce actually a velocity for the wave function. So you actually induce a current if you connect this system to an electrical circuit. So you have, if you view the drive as being one of a classical system, you're driving your system. So that means you have a dynamical classical variable coupling to your quantum system. And you induce a current, so that means if you couple no electrical circuit to your 1D system, you're going to induce some change of charge in this system. The Thouless pump is nothing but, again, the same phenomenon where you're pumping from the cavity that's driving your system and injecting the charges in this electrical circuit. You can apply then these ideas also to one-dimensional systems that were proposed recently to have a topological response. So here, an island, a multi-terminal Josephson junction between several superconductors at different phases. And you can look at what's called transconductance, so the conductances between different superconductors. And recently, actually, it was proposed that these transconductances are again quantized, and this quantization is again a Chern number. That's just the same physics, and again, the same formalism applies to these ideas. And there was another proposal to realize a topological frequency converter, which is just the same idea, but in a different context. What we've done here is basically realizing that the same physics occurs in systems of different dimensions, physical dimension. You don't need to be in 2 dimensions to have a response which is analogous to that of the quantum Hall effect. What you need is to connect your system to 2 independent probes, and in a way which was naturally realized in the quantum Hall effect. But what's constant here is the number of classical variables to which you couple. So that means that a priori, I can do it now with the simplest quantum system, a 2-level system coupled to harmonic oscillators. So that's a path to realize this kind of physics with quantum circuit quantum electrodynamics. So with just 2-level qubits coupled to microwave cavities. So what are we going to measure if we realize such a system? So imagine here we have a quantum system coupled here to 2 waves, 2 classical waves. Then actually the equation I've written was actually a change of a charge here of one of these cavities. But for a cavity here, I know that the energy is n times omega. If you increase n, that means that you're transferring energy from one cavity to the other, from one mode to the other one. So actually what we're going to get is a power transfer from one mode to the other one, which is quantized, and quantized in terms here of a Chern number. So the goal is to realize here a power transfer between these cavities, which should be actually quantized in some limit. How can you realize it? So as I said, the simplest system you can think about is one of these qubit 2-level systems, so a spin. And you know that any two-level system Hamiltonian is parameterized by three real numbers, so parameterizing the x, y, z polymatrices, parameterization of your Hamiltonian. So that means I can view this Hamiltonian as being parameterized by a three vector. What do I need? I need the system, whatever the value of my phasors on both sides, to be gapped. So this vector shouldn't vanish for every value of the phasors. And I need it to be topological. So topology in that sense acquires a very visual actually meaning. As phi1 and phi2 evolve on the torus, this vector then is going to map the torus on a closed surface. This closed surface cannot actually close the origin because of this gap condition. So either this closed surface winds around the origin or it doesn't. If it winds, you have a topological gap phase. If it doesn't, you have a trivial topological phase. Okay, that's simple physics of a topological spin. And so that's the condition we need. If you go and ask your experimental friends to realize such a system, they will run away. Because that requires actually to have here coupling. So here you have a two-level system, and what you're asking is transition amplitude between these two levels to change smoothly in time in both the x and y direction independently. And that's extremely difficult to realize. In one direction, that's doable. To have it in two different directions independently, that's impossible to realize. So you have to resort to a different way to realize this physics. So what we've proposed actually is a way to realize this two-level system effectively by using a third level. So by using what's called a Q-trick. So a three-level artificial atom where you have here two levels, and we're going to use the third level actually basically to implement all the transition between these two lower levels. So by perturbation theory, you realize that if these two levels are very close to each other, then actually you can induce effective couplings through the third level. And so we have, I won't describe in detail how to realize such a system, but a priori, our proposition is doable. Actually, we are working in close collaboration with an experimental group. And so, as I said, so you can actually look at the topological properties of this model on general ground. What you're using actually this model actually is nothing but the block Hamiltonian of a Haldane model on what's called the Lieb lattice. So that's something which is easy. That's standard actually to analyze. We know that when it's topological, when it's not. So that gives us condition on when actually this system is topological in terms of the coupling amplitudes. And as I said, in the limit where I have two levels that are very close to each other with respect to the third one, you're just implementing a topological two-level system effectively at low energy. And so in doing so, actually, we've slightly modified what we should measure. So there's a slight complexity in doing so because now we have three baths, actually. We have three levels, we have three frequencies corresponding to the three different ways we're going to drive the hopping amplitudes, but actually these three frequencies are related to each other. So if you worked out again what I was describing, the relation between the charge of the bath, you realize that now I have a relation between the sum of the change of the sum of two charges and the difference of two other charges, because just looking at how the frequencies are distributed on the bath. That means that if you want to detect the topological transfer, you should consider this quantity. So divide actually the power transfer by some combination of frequencies. Until now, so we have only a numerical study, not yet experiments on this system on how to implement it. So here that's the phase diagram for some values, optimal values here of all these coupling amplitudes. What I'm going to show is basically how it evolves when I change just omega 1, 2. So that's just the amplitude of transition between the second and first excited states. So when it's too small, actually, what you get is a gap system, which is trivial. The Chern number is 0. When you have a phase transition where you close the gap somewhere for some of the phases, and then you have a topological phase. If you look now at the power transfer between the different environment, and you hook up this effective charge I was mentioning, then you find no transfer, as it should. So that's not a topological transfer. On average, you don't transfer energies between the baths. On the other hand, if you now consider the topological case, if you drive strong enough actually these two levels, then you should here see a power transfer between two baths. So you're constantly in time actually transferring the energy from one combination of baths to the other one. If you look closely, we don't have a perfect here quantization in time. And why is it so? It's because actually the adiabatic approximation is not valid on longer time. So we have a limit time below which we should be able to measure this rate, this power, and that's directly related to the amplitude of the gap. So that's a limiting factor for this two-level system. The larger the gap, the more stable is the pumping. So far, so good. So that was just classical physics. Now I'm going to, and it's very natural, to look at what remains of this coupling between my two harmonic oscillators when I consider them as being quantum oscillators, so cavities, real cavities. In that case, I know that I don't know whether the system is topological. Topology was related here to how the eigenstate of my quantum system behave when I change the classical variable, which are the phase of my environment. If they are quantum, I don't have now to start with a Berry curvature. I don't have a Chern number. I don't know whether my system will remain topological. But now I've related this topology to a physical property, a pumping of energy. So I'm just going to consider whether I still pump energy from one bath to the other one. That's a hint of whether there's some sign remaining of this topology of the initial system. How do I quantize my system? So until now, I was actually coupling to some phasors. And I have a problem of how to define properly the phase of an harmonic oscillator. The quantities which are naturally defined actually are the square root of n times the sine of this phase, square root of n times the cosine of this phase, which are nothing but the momentum and position operator of my harmonic oscillator. So that naturally actually hints to replace this coupling here by something which depends on the filling of my harmonic oscillator. So instead of this coupling gamma 1 and gamma 2, I'm going now to consider something which couples to a bath with a strength that depends on energy inside this bath. That's the square root of n, square root of n2. Okay, so I replace my initial quantum Hamiltonian coupling to classical variables by this quantum Hamiltonian, but coupling in a different way to classical variable. And then I have, without any further work, actually a quantum correspondence with Hamiltonian of a spin coupled to two harmonic oscillators, very simple Hamiltonian. So this has some consequences. If I look here at the phase diagram of my initial domain, instead of gamma 1 and gamma 2 for m equals 1, so you can fix the amplitude, the origin of energy, instead of gamma 1 and gamma 2, I had this initial phase diagram, topological gap region, non-topological region. But now if I consider the second classical Hamiltonian, because my couplings depend on the filling, I have a direct signature of topological nature or not of my system, depending on whether or not I'm going to evolve in this initial phase diagram. If you start outside here in this non-topological region, your coupling amplitude, because N1 and N2 don't change in time, you don't pump, your coupling amplitude don't change in time, you stay where you started. You start in the topological region, because you're pumping, because you have this Chern number, that means that this coupling are going to evolve. Let's say you're pumping from bath 2 to bath 1. You start here. You're going to evolve into this topological region. That's for the classical case. What about the quantum case where on first ground it works? So you start here. So that's just a way to represent the evolution of a quantum system. Again, a very simple quantum system, but projected onto this phase diagram of a corresponding classical system. You start here, and you start actually evolving in the topological region. I didn't show it, but in the non-topological region, you wouldn't move. You start evolving, then actually you cross the topological phase transition where the gap vanishes somewhere. Instead of crossing it, the system actually jumps to the excited states. Because the gap is very close, then you have a Landau-Zinner transition on a very short time scale. So you actually, it excites, but then the Chern number of the excited state is exactly the opposite of the Chern number of the ground state. You start pumping in the other direction. Okay? So that's on first approximation, that's a quantum pendulum. So you pump in one direction, in the other direction. That's what's represented here, where I consider the number of quanta in the two baths. So you have the first series of pumping and then the second series of pumping. But that's not the end of the story. If you look at longer times, what you get actually is a damped topological insulator. It doesn't actually oscillate constantly in time. Why is it so? Because at any transition here, you don't jump fully in the excited state. I mean, that's a quantum evolution. You don't have a transition where you jump fully in the excited state. And so you start actually circling, again, viewing the dynamics of this system projected on the phase diagram of a classical system. You start actually converging and towards a state here where you have very broad distribution of charges on the quantum environment, on the quantum oscillators. So here you have a first pumping, and then smoothly you evolve towards actually a steady state. And so this is represented here, where you have your initial phase, your initial eigenstate, quantum eigenstate, projected and represented in this way. You start evolving, so it's after the first transition, it slightly widens, and after, on longer times, it looks this way. So I didn't represent it fully, but then that means it's very natural to look at whether this notion of characterization of steady state reflects the different nature, the eigenstate of my fully quantum system. And the answer is yes. Whenever here you have such a steady state, that directly reflects the nature of the quantum eigenstate of my system, which still possess some property reminiscent of the fact that you were pumping in the classical case. So reminiscent of the topological properties of the initial domain. If you look at eigenstate with average N1, N2 outside of this topological domain, they look completely differently. So that means here we have a filter, we have a different way to characterize the eigenstate of a fully quantum system, depending on the topology of the initial quantum pump. And let me stop by thanking all the people involved at various stages actually of this work. So as I said, that's a collaboration with an experimental group in Lyon on quantum technologies around Benjamin Huard. I have to stress really the importance of the young people, the driving force of this project. Quentin Fischer, PhD student who now left JQI. And on the theory side, actually, several theory people were involved, but really the two younger people were Clément Dutrex, a postdoc who's now in Bordeaux, and an undergrad student, Jacqueline Luneau, on the last part of his talk. And with this, I will thank you for your attention.
Right, questions?
So if I understood right, you're really exploiting the Berry's phase of a two-level system to get this kind of coupling.
Yeah.
I'm just wondering, you could have more complicated versions of the Berry's phase, right? For example, you could have this non-abelian Berry's phase where you have degenerate levels. That so is there some analog of this? I don't know if you've thought about some analogous physical probe of the non-abelian Berry's phase of thought.
So the simplest version in the non-abelian case of what I've said would be actually, again, to look at the same Hamilton equation for the bath. So just change of charge. And then actually you're related to the trace actually of your Wilson loop. So again, to the something that doesn't really depend on whether you're counting the abelian, the sum of the abelian phases or the non-abelian, the trace of the non-abelian. And so that's for the sum of charges. The charges. But then a second question is, could we cook up actually other relation between these charges that would be sensitive to other aspects of this non-abelian and or other symmetry protected actually aspect of these Wilson loops? And we don't know yet. We've tried, for example, with time reversal, and it's unclear now. What can be done actually, and that's natural, is out of this Berry curvature is a second Chern number. So yeah, Chern number of a four-dimensional quantum Hall phase. That means now we should use actually 4 different probes because the dimension is, and it works. You have to work out really, but the difficulty is always the mapping the topological index to some observable which is easily detectable. And that's always the trick. That's really what comes out of this adiabatic evolution, and naturally, without any strange manipulation of the observable. And that's I don't have a general answer on this.
If I understand correctly, you are pumping Cooper pairs, charge 2e objects.
Oh, in that system, but whose were Cooper pairs? Oh, in the case of the transconductance, exactly, that would be Cooper pairs. So when I say that this formalism applies to many different systems, it applies to these systems of transconductances, yes.
So in that context, I wonder whether Bogoliubov quasi-particles can be pumped, because they also carry the phase information.
Yes, yeah.
And is it possible to pump them like you pump electrons?
Yeah, so That's not my work. So that's the work of Yuri Nazarov and Julia Meyer and Manuel Uze. So basically where they look at, numerically, at the transport through different types of Josephson junctions, where you naturally actually include the Cooper pairs transfer, but also this excitation, these quasi-particle excitations. And what they found actually is that very generically, they were dominated actually by this kind of transport. As a function of the different phases between the superconductors. That means now you have a very large phase diagram where you have many, let's say 3 or 4 superconductors. You have a phase diagram depending on all the different phases. And so you sample this phase diagram and they realize that generically they were dominated by this transport and then the transconductances were quantized. In other parts actually of the phase diagram, you could be dominated by other quasi-particle transport. That wouldn't fit actually into this formalism. That wouldn't be topological. That would be a different type of transfer.
Any more questions? All right, if not, let's thank the speaker again.